Hello everyone! Hello, welcome to Geeks. We will go through how we discuss computing challenges in the context of high energy physics and then eventually presenting the initiative from INFN and Intertwin that you might know very well, so the interLink software. What is CHEP? First of all, very quickly, you might have heard, for instance, of the one of the main initiative in high energy physics that is the CERN experiments, so the CERN accelerator called LHC. And in fact, around these experiments, there are a lot of communities and a lot of data to be analyzed because we make this accelerator such that can take pictures of infinitely small events but they produce a lot of energy. So, and with all this energy, there are a lot of secondary particles that are created. You can imagine like something that crash and it can explode in multiple pieces. And to reconstruct all this complicated stuff, you need a lot of data and analyze them in the shortest time possible. And to do that, historically, has been built a grid, so distributed resources to analyze this data. Different data centers around the world, analyzing a lot of data and transferring them all over the places. So you can see that the challenges in this context start to resemble the ones of huge industries or huge providers. So we are converging toward the fact that what is of interest for us usually has also some impact or has already been tackled in some other ways from other peoples out there. And this is why I believe that Segis can help. So, and this is why the podcast that I produce and I will share the schedule later on can be of interest. So because we try to tackle the gap between the technology side and the scientific side. With this in mind, consider CHEP conference like the place where CERN experiments and all other related to high energy physics presents their issue and their activity to solve them. You see that it's a 27th edition, so it's quite de facto major conference for computing in this context. This time it took place in Krakow and we were there participating. Just to give you an idea, let me switch the presentation mode to this biggest one. Okay. So just to give you an idea, what are the main challenges that we have? So the scientific program is like this one, I hope you see clearly. So it's data and metadata organization. I'll try to organize an episode of the live podcast with people that are working around this data management stuff. I think it would be useful. Then there is online or real-time computing, offline computing, so two different kind of data analyzing needs. Real-time means, so this online things is because I mentioned before that you produce a lot of data, you have to scheme, you have to trigger on different parameters to be sure you cannot collect all the possible stuff. So you need to select online what you want to analyze later on. And the offline stuff is okay. I have my top-notch data triggered and stored somewhere. I want to analyze them to do to test my hypothesis, my scientific hypothesis. All right, distributed computing. It's also it's the track and the fact that we were looking at before. So we had a grid of computing resources. We want to be sure to scale out as soon as we are sure of what we are doing in our analysis, to scale out in all the distributed resources that I have available to shrink the time needed for analysis to complete. Alright, so then there are simulations to compare what you expect with what you measure, and then there are a lot of stuff. So you have an analysis, you have results you want to share with other people, and so it's important how we collaborate and maintain software and analysis pipeline in a comprehensive way. Then we have technology to manage computing infrastructure like interLink, so how we can create a continuum of resources. Let's just wait a few minutes, I'll explain more. Alright, then there is collaboration outreach. Of course, it's important, as we are doing right now, to make people understand what we are doing. And actually, the analysis facility and interactive computing that is strictly related to the computing infrastructure. And it means, okay, our needs as a community that do data analysis are evolving, and new data science frameworks are capable of exploiting cloud resources, not as well as our HDC distributed resources. So, or neither our HPC supercomputing centers. So what we can do about that? So, and yeah, all these activities rotate around the idea that you can integrate somehow, you can expose to the user the simplest interface possible, and then take the charge to distribute the payloads where they belong to. I hope this introduction makes any sense to you guys, and then if not, let me know in the chat. I just wanted to make, okay, yeah, I mentioned before how many centers we have, and then I want to start directly with introducing, whoops, sorry, never got the correct one. Okay, to introduce the work that I presented there. So, as you can see, the main objective that I have and I want to share with this channel and to convey is that we might have a way to coordinate payloads that runs on cloud resources with the ones that can access a lot of tons of GPUs on a supercomputer, for instance. So in other words, we want to put ourselves in this situation, right? Where there is a continuum, and yeah, I know this is a buzzword, but this is a continuum where on the left-hand side, you have the heterogeneous use cases. So you, as a user, want to do different things, starting from having your results ready in the time of a coffee break, after you deploy your models on a cloud resources. So you want to start on cloud, when ready, go as fast as possible. Then you will also want to model your online computing in some sense, or your reconstructions or events. So you want to get GPU accelerated workflows with a norm to develop easily and then deploy at scale, on grid in this case. Same behavior is for machine learning training and inference models, and we all know that in the industry it's already accepted, but also now in energy physics we will see that this is a use case that cannot be neglected at any stage. Eventually, we do have, and we will have, analysis that runs, or particular workflows that runs as they are running today. So on the grid sides, we cannot get rid of one of the three components. And the three components are in the bottom right here. So are not only differentiating by the kind of by manage that. Computers, we have usual Slurm batch system and a lot of GPUs and NPUs, a lot of computing power. Okay, On the HTC side, you still have a lot of computing power focused on classic GPU, CPU, and RAM. GPU is an Italian one, and they are managed by different systems. So HD Condor, Melee, Arc, and whatever else. The last one, but is the one that interests more the latest users, is the cloud computing part. That, like it or not, is converging toward I want access to a Kubernetes cluster or to a framework that under the hood is talking Kubernetes APIs language. Yeah, we are accepting the fact that ML workflows and GPUs are not negligible at any level of our infrastructure, because you can see here there is a list of talk that at this chat talk mention machine learning. There are plenty of even more if you do the same. And yeah, where are our resources? Where are our accelerators when we need it? And yeah, joking apart, we should and we could already access HPC supercomputers as a scientific community, and we do to a certain level, but it's a painful experience, especially if you are expecting to arrive with your data science framework of choice, right? Because they are not pretending, but they are taught with Kubernetes access in mind. And more often than not, on HPC resources, you do not have access for Kubernetes APIs to install a Kubernetes node. Well, we can do that. Well, we started from the experience that we have at INFN, that is the National Institute for Nuclear Physics in Italy, to extend our grid site towards cloud resources. And yeah, we have a lot of experience in that since several years, but the trigger of the activity of interLink creation was we had two playgrounds, perfect playgrounds for this development. The first one is the Italian Center for Supercomputing, Big Data and Quantum Computing, called ICSC, the most difficult acronym ever. And it collects not only scientific use case, not only nuclear physics, but it brings together, okay, we have a lot of distributed resources. We want all scientific domains to be able to access them, just like we are doing for high energy physics. So collect all these behaviors in a single interface. It's very challenging, as you can imagine, but the challenge is shared with all other set of stakeholders, if you want. And one of those stakeholders are tackled into the European project that we are participating and where interLink born, that is called interTwin. interTwin is a digital twin engine initiative. So the idea is to create an interface to develop digital twin applications of any kind. So starting from high energy physics, you want twins for your detector, so you want to simulate how they behave. But also there are other use cases, like I want to simulate weather, I want weather conditions, I want to simulate fluid and understand the risk for fluid in certain places. All of these go into the same basket, and the interTwin project started collecting and trying to find a minimum common denominator for all this kind of initiative. All right, just supposed to take a bit of a breath. There is not all yet then indeed in this initiative, and we needed to keep that in mind. We need some modular and adaptable solution. Oops. Okay. What was our strategy then? Well, you can see that if we are brave enough to say that all our use cases, all the people that want to use this technology should be able to talk Kubernetes language, that it's a good bet, I think. Sooner or later, this can be repaid. Then we can imagine to introduce a concept of a virtual Kubernetes node. So we want to hide any custom logic to the users. So in other words, the user arrives with his pipeline, then ask Kubernetes run this pipeline on a node that has some particular label on it, okay? And then at this level the magic happens, because the pod execution request is translated into something else that allows to talk with a remote site that it might be, okay, it might be a GPU node on an HPC center, so on a supercomputer, calculate my results and get back to the users. Again, I'm trying to be clear, the Kubernetes API layer is just the common denominator. On top of that, you should build your user platform, right? So the offloading mechanism, that is the one responsible to take your pod and bring it to another level, is just the interface that we put in common for all other use cases that can build on top of Kubernetes. Okay. Yeah, I don't know why it's not changing. Okay. Okay. I make a bit of confusion with the Windows, sorry. And then we got to discover that this kind of abstraction in Kubernetes was quite interesting, because it was already there since several years, I think. There is a project in the Cloud Native Computing Foundation sandbox that is called Virtual Kubelet that does exactly that. So you take your Kubernetes cluster, you can put whatever you want, whatever user framework you have, and as soon as an application arrives with a request to run my container, you can include a virtual node, okay? So in other words, you are keeping your Kubernetes API, and underneath, under the hood, you can define a custom logic and emulate the behavior of a normal node. So you can tell, okay, I have this amount of GPUs, I have this number of pods running under my umbrella. Else can be customized. Pretty cool, pretty useful, and in the time where Gen AI and GPUs are gold, you start seeing this more and more. Not in science, but for instance, in commercial application, you start seeing this more and more. And especially where you have providers that are fully capable of managing containers of any sort in a secure way. So I know how to run container. I have an API for that. So, hello, I'm Sophie. So yeah. So let me recap. I got distracted. Yeah. So I know from how can you access with a Kubernetes. It would take a lot of effort to implement everything from the top to the bottom. So implement and install your Kubernetes cluster on your well-tested, battle-tested infrastructure. Then how using Virtual Kubelet to abstract how you run containers from the cluster perspective. And this is what SAD, Fly.io, Classics, Devops, and also will have it. We are using Virtual Kubelet to leverage GPUs that are under different kind of management system. Very similar to our use case, with a huge difference that for us is critical. We have a lot of providers and there you cannot request them to be expert into Kubernetes internals. And to install and to create these different languages, you have to be very, very skilled. So you have to convince different sites to create their own providers. And this is something that we do not believe is a winning strategy. We need our providers to be in control, yes, to provide us with the way that they prefer their resources to be accessed. But at the same time, the skill level requested to create this kind of logic should be the lowest possible. And this is not the case for the native Virtual Kubelet provider interface. So we ended up creating interLink. interLink, you can imagine like a way to streamline the creation of Virtual Kubelet providers. Means the streamline to create in the most efficient way different custom logic for your virtual nodes. So, indeed, with this activity, we are setting up a contract. A contract means that you have a community effort to maintain all the abstraction layer that is internal to the Kubernetes. You can see here, it comes the normal interface for Virtual Kubelet and the capability to talk over network to a remote counterpart, to your remote resources. And then on the remote resources, there is a component that takes, okay, I receive messages in Kubernetes language, I translate them into container lifecycle instructions. So the only last mile that the provider has to implement in this case are simple Python script or Golang code capable of managing the lifecycle of a container through a REST interface. That's all. It's simple like that. Trust me. And as long as you respect this OpenAI spec, you are good to go. You can go ahead and say, okay, I'm a new provider, doing basically nothing but creating a few lines of Python or Go or whatever. So, did it work? Yeah, we tested. We are well aware that the worst case, the most difficult interfaces are the ones that are more closed. So we start with your HPC centers that were participating to intertwin. And in the first case was HPC Vega, where we ran all our initial tests and discussion with the administrators to understand how we can proceed and how we can get what we wanted. This was a fundamental stuff that demonstrated, thanks to the collaboration of the Slovenian administrator, that we can do through interLink, running containers from a Kubernetes pod into the supercomputing center. The other thing that we wanted to test was, okay, I have my containers infrastructure, so my container as a service infrastructure like Unicore at Ulick, and I want to apply my provider to this kind of interface. In other words, let me go back to this. I want to put my red box capable of talking Unicore language. So as soon as I ask run this container, I will ask Unicore to run this container. This worked like a charm, and in few weeks they were capable of providing their own plugin. So this was the second success that we have in interLink. We demonstrated that we can simplify the life of our providers. Yeah, it worked. I can answer the question in the title. It worked pretty well, and so well that we now have a lot of other use cases that are trying to evaluate this. The main use case was again from InterTwin project, and is from CERN. CERN, if you remember well, is an HEP initiative, energy physics. In this case, there is a 3D Gunner algorithm that was able to run a supercomputer and report back the results into an ML flow tracking server. The task was offloaded to Vega and Ulic with different kind of configuration, of course. You can imagine that each HPC center has a different option to submit their Slurm jobs. So you maybe cannot see here, but you can see in the documentation of interLink that to access a virtual node you have to specify node selector interrelation just if you like you would in a normal HPC, in a normal Kubernetes node, and then you can have different pod annotation to specify what are the options for the Slurm submission. This pod annotation stuff is pretty powerful because you can pass information to the remote plugin and evaluate this information in a custom way. In other words, you can prepare your pod to be executed on a supercomputer with different parameters, just leveraging annotation. So you can reuse the very same pod in different endeavor where the annotation will be ignored. And it's particularly handy where you want to run pods distributed on different nodes. Alright, so we started from HPC resources, that's right. What we did then is, what if with this abstraction we create a Kubernetes cluster, seed of resources for our users, and then we provide them the access to all the different resource management system that we have in Italy, for instance. In Italy, this is done in the context of analysis facility. Remember from the beginning, this initiative focused on creating fast turnaround analysis. So we extended a Jupyter Lab instance or a continuous integration script of the users, specifying, okay, this task should run on a virtual node that is running on the grid, on the Italian tier grids. And yeah, it worked like that. So it's working. We federated in this way all the Italian sites for the analysis, and it's working. So users are not aware, well, are aware, but they do not know how, that they have access to this kind of sites. So they import data on that sites and analyze them using pod definition or frameworks that runs distributed, so like the DAS scheduler. There was also a nice talk from Matteo at CHAP where he's shown another application, another federation availability for interLink that allows you to federate HPC resources with HT-Conda resources with tiers, so with distributed sites, and also add beefy GPUs. So we complete our triad here, right? You see, there is HTC resources, there are Slurm HPC resources, and cloud. You can create on cloud. We have also video in the past, and we will have more in the future, where you can bring up a machine and install them into your Kubernetes cluster like a virtual node. This is possible. This is possible now. The only requirement is Docker engine running on the machine. And so we did, and so they did at AI and FM. And now they have access with the very same portal to all these kind of resources. One cool thing that is done at this level is that once you have this kind of federation, you can also manage your Kubernetes cluster through batch system frameworks like Q with a K. And yeah, that's cool because then you have a common batch system, but in a cloud native way. We will have a deep dive into that on also next episode very soon, so stay tuned. And yeah, eventually I mentioned before the ICIC situation, and there is a proof of concept already there to emulate these kind of scenarios in a more definitive manner. And also experiments like CMS are prototyping the implementation of creating pool of resources on these kind of sites using interLink. Sorry. Alright, now my preferred part. A maintainable solution is something that is accepted and needed by more than one community. And it looks like we are on the correct path. In fact, we are starting having interest from different communities, for instance from CNAS in France, about the LISA interferometer. So we are trying to create an Argo workflow execute plugin. Argo workflows is a technology already in a CNCF ecosystem to run simulation and evaluation in that context. Then we have Sir that is curious to say, okay, I have my Kubeflow implementation, my Kubeflow interface. I want seamlessly some of the part of a pipeline to be run on a virtual node. How can I integrate this? And this is a very cool project ongoing with CERN. And the last point is also very interesting because there is a provider that is called NewNet that is giving access to a distributed kind of resources around the globe, and it wants also to allow users not only to run containers or payloads, but to give access to them through a Kubernetes API. How you can do that in the simplest manner? Well, surely interLink is one of them. In fact, they are evaluating their own plugin. They are working on their own plugin. So yeah, I think this is the most celebrative overview. So we were in the middle, you see, we developed interLink, and we are successfully at the moment, we say, managing all the heterogeneous scenario, both from the computing user side and from the computing provider aspects. So yeah, it looks good and it feels also good. Then let me go ahead. Yeah, and this was the summary. So, but I can do the summary in this way. Yeah, don't get me wrong, there are a lot of things to be done yet, but we are confident that this might be of interest for you to try out, whether you are running on your provider, you want to give access to a Kubernetes API, or you have any kind of machine VM that you can provide with GPUs and you want to attach them to your Kubernetes cluster. So any kind of container-based use case can run on this. There are some limitations that you can find in the documentation. Yeah, we are eager to hear from you what you think. If you have any use case, just jump in the Slack channel or message me or whatever. We are here to help, and also developing new more modern and complete documentation and developing SDK kit. And yeah, we are hoping to apply for contributing to the Cloud Native Computing Foundation Sandbox soon, so to manifest our willingness to be open to contribution and to stay like that. All right, so I think we are just in time with the idea to have a very quick live. I don't know if there is any question. Okay. I see this during the stream. I can answer later. So, okay then, since we are here, just a couple of, just a couple of questions of news. The first one is that the next podcast will be about Lico and how they're using virtual kubelet to federate two Kubernetes clusters, two or more Kubernetes clusters, and how this helps for federated learning, for instance. That will be very cool, so stay tuned. We will have another episode later on with Ricardo Roca from CERN, where we talk about MLflow and all its application with virtual kubelets. And then to be defined, there is other episode to be scheduled. One is from the communities that are using Kubernetes or have different challenges. I like to have one on data management, and yeah, we will see. I'll circulate the schedule very soon, so don't worry. That's all, guys. So thank you for joining and tuning and looking at this video. If you have any question, any kind of question about interLink, just drop me a message in any way you prefer. So thank you and see you in the next episode.